Okay, so let me just like quickly recall what we talked about last time, right? We talked about the modular space of curves, smooth curves, called MGN, and we defined a compactification called MGN bar. This was the modular space of stable curves. And we said that there is a stratification of this. And so recall was a disjoint union of various strata, and these were like the modular space of curves whose dual graph was isomorphic to this this stable graph, right? Gamma was a stable graph. And one thing that I think I said this, but maybe never didn't really write it down, is that the codimension of the strata is actually equal to the number of edges of the stable graph. Okay, so as you create more nodes or no more edges, you go like deeper in the boundary. Okay, and let me just let me just do. We looked at an example of stratification. Let's just do one more, just so that we're kind of comfortable with this. Let's do M12 bar. Okay, so first of all, what's the dimension? 3g minus 3 plus n. And that's g is 1 and n is 2, so 2. And the biggest strata, of course, is always the, okay, so let me just kind of index this by codimension. Codimension 0. The biggest strata is just the smooth curves. And the stable graph, in this case, looks like a genus 1 vertex with 2 mark points. Okay, and let me just kind of write the modular space on the other side. This is just smooth curves, right? So it's 1, 2, and 1, 2. And then remember that we sort of have two things that can happen. These 2 mark points can come together, in which you create a genus 0 bubble, right? So in codimension 1, you have this kind of stuff. And you can pinch the cycle. So in fact, you also have the ones that look like where you have a genus 0 vertex, something like that. Okay, the first one is looks like M11 times M03, and the second one is like M04. Right? There's four half edges. Okay, and then finally, codimension 2, it's the lowest stuff. Well, you can take this graph here, right? Take the genus 1 component and pinch the cycle. So you get that. Or you could take this and bring these 2 mark points together, right? And then you get exactly also the same thing, because those 2 would just bubble off into another genus 0 component. Okay. So that's what the stratification looks like. Okay. So then let me quickly go through. Well, first, some of these some of the maps, the natural maps between the modular space of curves. We already saw the first one yesterday, called it the glowing map. So again, I take a stable graph of type Gn. The glowing map is a map that basically glues. Okay. Yeah, what you do, right? Remember that you do keep track of the. Okay. Let's see what some of these look like, right? For example, bit of like genus G with some mark points and some points that you sort of remember. Let me put them here. And for example, one of these glowing maps would just take it and glue these 2 points together. So it gets okay. So for example, this is a glowing map that takes something in M3, 2, 3, 5. 1, 2, 3, 4, 5 mark points to something in M4. Okay. These are the type of, I mean, this is one type of glowing map, right? You could be glowing. So this is a glowing map. If you would, your stable curve would just have like one component, something like, for example, this thing, right? And then you just glue it. You can also glue different components together, right? If I would have, okay, I'm not going to draw it, but if I would have another component, if your stable graph had like another vertex, you would have another component, and then you would glue that one together to this. I hope that's clear. Okay, and then the other map that we need is the so-called forgetful map. Forgetful map I'll denote by P. It's a map from, okay, this is an example. mg1n plus 1 bar to mgn. And what we'll do is just take a curve with n plus 1 mark points, stable curve, and just send it to a curve with n mark points, right? Just forget the last mark point. Okay, but when you do this, you have to be careful. Yeah, everything's bar. Thanks. And the reason that you have to be careful is that you might forget mark point, which would make some component unstable. So, for example, what could happen, right, is you'd have something, and then with a bunch of mark points, let's say your Pn plus 1 is kind of sitting here, and you have some other curve here, doesn't matter. And then you forget Pn plus 1, right? And then this component no longer has 3 mark points, and so it's unstable. And so what do? You have to contract it. Okay. So what do? So you send it to this guy, but then this component that became unstable, you just contract it. Oh, they're touching. So really what you do is not just forget it, but you stabilize it, which just means that if you had something unstable, then you just contract it. And it doesn't happen all that often. It basically happens in this situation, or it could happen if you had just something that had, let's say, Pi and then Pn plus 1 here. And then this one, you would just send to, so yeah, again, when I forget Pn plus 1, right, this becomes unstable, and then you just contract it. And then the point where you contract it to, you just identify that as the mark point. So I guess here should be Pi. You just put it on the thing where you contract it. Okay. Okay, remember that our goal is now to do some intersection theory on ng and bar. Okay, probably I should have kept that. Let me keep that. Okay, so our goal is to do intersection theory on MGN bar, right? So we should be looking at the cohomology ring. In fact, we'll look at a sub-ring of the cohomology ring called the tautological ring. As it turns out, the tautological ring contains like pretty much all the cohomology classes that you can write down geometrically, at least. Although it's pretty small when you go up to higher genus, that's where we'll work, and it's much more tractable. We'll see in maybe like the next half an hour that it's like very tractable. You can actually do computations there somewhat explicitly. Okay. Okay, so sort of the study of the tautological ring was started by Mumford. And Mumford, well, wanted to study something that he called like the most important cohomology classes. And well, we've already seen some of the cohomology classes that we want, right? I mean, there's an obvious one, which is like 1, right? What is 1? It's the Poincare dual of the full thing. Remember that it's always in codimension, so there's a Poincare duality. I won't write it all the time, but if I would write down if I would write down some submanifold or suborbifold or something, then remember that it's always a Poincare dual of that thing, and so it's living in codimension. Say 0. And we've seen that the image of remember that the image of this map was actually the closure of the strata. Right? We'd like those things as well. So we have some really nice subspaces, let's say, in MGN bar. We'd also like to have the cohomology classes associated to those. So we would like at least closures of these things. Okay. And remember, again, codimension is the number of edges. Okay, and now I think I can write down the definition. Oh, sorry, there's always a 2, just because it's going from like complex to real. Okay, I can write down the definition of the tautological ring, I guess, here. So the tautological ring denoted by R, H star, and G n bar. It's a subring of the cohomology ring. Okay, that's defined as the smallest subring is the smallest. Okay, so I'm sort of defining all of them at the same time for every G and N. It contains all the units, so all the ones. Okay, so I write it 1 because it's the unit in cohomology. And is closed under push forwards by the glowing and forgetful maps. Okay, so well, what do I mean, right? Let's kind of think about this definition a little bit. First of all, it's defining all of them simultaneously, right? Because if I would take push forwards by glowing and forgetful maps, remember that I'm going to go to some other moduli spaces. Secondly, what does it mean that it's defined as Q subalgebras? It means that if I would have two tautological classes, and I take linear combinations of them, or I take products of them, then they're still tautological. Okay, so work. If alpha beta tautological, alpha tautological, consequence of the definition. Okay. Oh, and the second thing is that we said, okay, now I already have these ones, right? Because, well, by definition, I have the ones. But I also said that we would like, we've only basically seen really like this one nice subspace in MGN bar. And we would like to have that as well, right? But we do. So the second remark is that it's not totally obvious from the definition, right? But these are also are tautological. And the reason is that I remember from yesterday that I said that if you take these glowing maps, right, for any gamma, and you take the push forward, so the image of the glowing map was in fact exactly the closure of the strata. It just had some degree. So so in fact, if I would just push one, right, which you think of as just as the product of all the ones from all the different MGNs in the stable graph, and just divide by the automorphism because of the degree, this is actually equal to. Okay. Okay, so we're, yeah, I mean, hope this is clear. So one means like take, remember that we're really working on, so the glowing map, right, the domain of the glowing map is like the product of the moduli spaces of each of them associated to each factor of the vertex, right? So one means take all of the ones, like pull them back and multiply them together and push it forward. Okay. And then the image of the map, right, we said is just the closure of the strata, but it had some degree, so you have to divide out by this automorphism. Okay, but yeah, I mean, it's a nice definition, right? But it's somehow pretty useless. Like you can't really, I mean, if I give you a cohomology class on MGN bar, you don't really have a way of saying if it's tautological or not. But actually, I mean, the whole point was that I said, oh, well, actually, if you restrict to the subring of the tautological ring, you can do things explicitly, and you know much more about its structure. Okay, and in fact, that's true. It's just not obvious from the definition. In fact, what we can do is actually find a basis of generators for the tautological ring. Okay, that's what I'll talk about next. Okay. Okay, now we need to look at some cohomology classes. So the first one is going to be the so-called psi classes. Probably you've already seen these or heard about these at least. And the way that these are defined is that you look at a line bundle, we call it Li on MGN bar. It's called the cotangent line bundle. Cotangent lines. Ith cotangent line bundle. I is something from 1 to n. And the line bundle is defined such that if you take the fiber, right, so if I would take the fiber at a point on the moduli space, which is a curve, it's a stable curve, bunch of marked points, that's just the cotangent space of the curve at the ith mark point. Okay. Okay. And these things like glue together nicely to actually give you a line bundle on engine bar. And the psi class, so definition, psi class is just appear all the time. The psi class is just defined as the first Chern class of this line bundle. Okay. And you see that it's the first Chern class of a line bundle, so it's going to live in codimension, like it corresponds to something in codimension 2, right? Real codimension 2, complex codimension 1. Okay, so that's one of the ingredients that we'll need. And a fact that I will not prove is that psi classes are tautological. Psi I is tautological. Okay, so psi I. But in fact, at least in genus 0, psi classes have a pretty nice expression. As the Poincare dual of some codimension one thing. So what is that? Okay. So maybe a second right here. In fact, in genus 0, you can write the psi class, right? Psi I. So first you pick. Okay, so I would like to get an expression for the psi class. So what you do is that you pick some j and k that are not equal to each other, and so we're in M0 n bar, and that's not equal to I. Okay. And the psi class is an expression that looks like the Poincare dual of some of these divisors. So I have two genus 0 components, right? I'm in genus 0, so everything is genus 0. And it's a divisor because it has just one node. And I put my I on one of the components, and I put my j and k on the other one. Okay. And I sum, and then I still have like n minus 3 of these mark points to put somewhere. So let me put them basically in all possible ways. So I'll say I, j, and I sum over I and j. It doesn't matter what j and k you pick. Okay, just pick any. Okay. So in fact, you can use this. To compute some things, some intersection numbers. So we'll compute our first intersection number now, I think. Yeah. So let's compute an intersection number. So what is an intersection number, right? I take something so I'm on M04, and I want a class in remember that the dimension is 1, right? So complex dimension 1, real dimension 2, and I want something in the top degree, so I will just take one psi class. So let's compute this guy. Okay, how do I compute it, right? So I told you what does the psi class look like. So psi 1, I'm just supposed to pick two other points, right? So I'm going to pick 2 and 3. And then my psi class, psi 1, Actually, I said, okay, put something of genus 0. Something genus 0. Yeah, sorry if that's too small, just please complain if you can't see it. And I picked 2 and 3 and I put it on the other thing, right? Okay. Well, now I still have 4. That's the only thing I have. So you think I could put 4 here or 4 here, but you can't put 4 here because then this is unstable. Sorry? It's unstable. Yes, exactly. Thanks. And so I mean I should have said here that you want these components to be stable. Okay, so really all you can do is put 4 here. Okay, now what is the integral? I said, oh, when you're integrating, right, use point carrier duality and you just like count the number of points. It's the degree. And so, well, here there's only 1 point. Okay. Okay, remember M04 is just a P1, right? And I'm saying that the psi class is just his point carrier dual to a point, right? There's just 1 point. And so the integral is just 1. Yeah, if there would be 2, you'd get 2. We'll do something more complicated in a bit, I think. Okay, I should probably have kept my definition of the tautological ring, but now, okay, so let's go back to the general stuff. Well, if I have psi classes, I said the tautological ring is stable under push forwards, right? So if I push forward a psi class, I should get something that's tautological. And these things are called kappa classes. They push forward under the forgetful map. So remember that P was a forgetful map, and then we defined kappa A to be the push forward psi n plus 1. Okay, another thing that I should say is that so far I was kind of writing, when I was taking products of cohomology classes, I was writing like a cup. I'll just not do that anymore because it's annoying. And I'll just kind of write it like you write it in a ring, right? And just multiply it together. So this is like the psi n plus 1 class multiplied like 8 times together. A is from 0. A is something that's greater than or equal to 0. And this is called a kappa class, and it lives in A plus 1. That's an H2A chain bar, where I remember that P is just a forgetful map. Oh. Okay. So this is something we need in the tautological ring as well. And we're almost there. This is, R. Okay. Classes. The last thing we need is these things called decorated stable graphs. Okay, so now I have psi classes. So, okay, definition. Okay, so what's the last thing? Right, so definition. A decoration. Stable graph. Gamma is an assignment. Is a class. It's an assignment of some class I'll call alpha in, right, remember stable graph is of type GNN. It does all these components. We have all these modular spaces. Or in such a way, let me say 2 first. You put you're allowed to put psi classes on half edges. Right? So alpha is just a product of psi and kappa classes. And these kappa classes, you put them on vertices. Okay. So for example, a stable graph, a decorated stable graph looks like this. I think I can do it here. So okay, and I will denote the notation for this will be okay. And these are also tautological classes. RH star. Okay, so let me first write an example of. Let me try to draw an example of what a decorated stable graph looks like. Hopefully that will clarify the definition. Right, so first I have the following graph. I take a genus 3 vertex, take a genus 1 vertex, and I put some mark points. And let me just label these mark points, right? So I have 3 mark points. I'll label them 1, 2, and 3. Okay, this is a stable graph. And then I'm allowed to put psi classes on the half edges. So for example, I'll put a psi class here, a psi class here, right? These are also half edges, remember? Call it psi prime, psi double prime. And I'm allowed to put kappa classes on the vertices. Okay. So to this vertex, I will associate a kappa 1. Okay. So for example, this is a decorated stable graph. Okay, how do you think about a decorated stable graph? Okay, so let's do a couple of things, right? So how do I think about a decorated stable graph as a cohomology class? So remember that we have the gluing maps, right? This again comes up. Okay, first of all, so on each of these vertices, each of these connected components, I get a cohomology class, right, in the tautological ring, which is just the psi classes and the kappa classes, the psi class and the kappa classes that I put at each of these vertices, each of these components. Okay, so that means in this case, right, what does this look like? I have M genus 3 mark points, M1, 2. Okay, on M33 bar, I have the following class. It's psi 2 psi prime squared. Okay, on our M12, I have the class that's psi double prime kappa 1. Okay, then what do? I take both of these classes, right? They live in the cohomology rings of each of these things. I pull them back to the product and tensor them together. Take the product, right? So I'll just write it as a box product because you pull them back from each of these factors and you tensor them together and you end up here, right, in the cohomology ring of this product. And then, okay, so let's do that. So now this I'm viewing as an element in the cohomology ring here, and then I push them forward. Okay, this gives you a class in the cohomology. Yeah. The alpha is just supposed to be a product of psi and kappa classes. Sorry. So alpha is just. It is an H, but yeah, but it's even yeah. Yeah, but I really want it to be only psi and kappa classes as well. So. Thanks. Yeah, thanks. Yeah, and moreover, alpha is a. Okay, I think it's better. Yeah. Okay, so maybe I say, maybe it's better if I would just write it as okay, so for every vertex I have some alpha v, and alpha v is only a collection of psi classes and kappa classes, where the psi classes are assigned to the half edges and kappa classes are assigned to the vertices. Yeah, thanks for the clarification.
But you don't need to assign to every vertex.
You don't. I mean, it could be 0, right? Yeah, that's right. Okay, so let's also do sort of a degree count here, right? So what's going on? So first of all, remember, psi classes are in cohomological degree 2. So the degree of this guy is 2 plus 1, 3 times 2, 6. So just this piece is going to be in a tautological ring of tautological ring 6 M3 3 bar. So that's like my alpha associated with this vertex. This thing is in, so again, the kappa class has, we said, cohomological degree 2. Psi class has cohomological degree 2, so it's in degree 4. Okay, so when I pull it back and take the product, I get something in cohomological degree 10, 6 plus 4. And then I push it forward, right? And remember that when I push it forward, I still have some codimension here to worry about, right? This is not, this map, the image of this map is living in codimension equal to the number of edges of the graph. How do I get 4 again? So it's the kappa class that is in degree 2, and the psi class that's also in degree 2. Okay, it's 2 plus 2. And okay, so when I pull it back, I get 6, like I get something in 6 plus 4, it's 10. And then I push it forward, okay. And then I push it forward, right? And when I push it forward, I have to add by the codimension of the image of this map, right? Which is again equal to the number of edges, which is real 2. And so in fact, this class lives in 10 plus 2. Right. Was that calculation clear? Should I do it again? One more? Okay. So, okay, so what are we doing, right? We have a cohomology class on M33 bar, and we have a cohomology class on M12 bar. First, I want to know what the degrees of these, and what are we going to do? We're going to pull them back from each of the factors to this product, right? And then we are going to push forward along the gluing map to MGN bar. Okay. So now we want to do a degree calculation. So remember that psi classes have cohomological degree 2, and I have 3 psi classes, right? Psi 2, psi prime, psi prime. So 3 times 2 is 6. So it actually lives in the degree 6 cohomology of M33 bar. This guy is kappa class is in degree 2, psi class is also in degree 2. Right? And 2 plus 2 is 4. Lives in degree 4. I pull them back and multiply them together. And then I get something in degree 6. In degree 6 plus 4 is 10. That's just 10. But in fact, that would be if I was looking in the cohomology ring of this product. But then I need to push it forward. And when I push it forward, this map, the image of this map also has some codimension. And so I have to add the codimension of the image. And the codimension, remember, is the number of edges of the graph. That's 1. Real codimension is 2 times the number of edges, right? So that's 2. Is that better? Yeah. It's just psi associated to this half edge, right? It doesn't have a name, so I need to call it something. But if you were keeping track of the half edges, right? Because your graph actually is keeping track of the half edges. It would be whatever number you gave to keep track of this half edge here, and this is the other half edge, right? Yeah, this is just notation for putting it on the half edge there. Yeah. Yeah. Uh, ah. No, I don't think so. But I don't know if I don't know if there's a way to do it, but I don't think so. Maybe someone else knows. They can. I don't think you can get it more explicitly than this. Yeah. No. Yeah. So no. Site2 has to go to the thing. I mean, remember that the half edges, right? They're going to sort of like keep their label even when you push them forward. So if it was like an edge that was 2, then it's going to be still like 2 here. Right? So basically, you put the site class that's just like with the mark point that it carries, right? So. Okay. So I hope that was okay. Okay. So and then the theorem is that's everything. So the theorem, or do I want to say it like that? That's true, but let me introduce a bit more notation before, I think. And here, so yeah, and the general formula here, right, for the degree now is that if alpha, which is now just a pullback, so alpha is like alpha v1 blocks, alpha v2, I don't know, let's say m, right? If this guy, okay, so just remark maybe. Alpha is in, it's just the calculation that we did before, right? It's in 2D engine bar. Sorry, product g of v and v. Then we will view the decorated stable graph like gamma alpha as something in the topological length of NGN bar. This will just live in degree 2D plus 2E, where E is the number of edges. Okay. Just to write down what we did in the example there. Okay, and then I want to let me define so-called strata algebra. To be as a vector space spanned by decorated stable graphs. Where you take the span over all gamma of type Gn and all possible decorations alpha. Okay. The one key thing to note here is that this is actually finite. Okay, why is it finite? Let's imagine that you would keep putting more and more decorations, right? The degree of the at some point you just get 0, because if you would go beyond the degree of the modular space, then there's no comodular. So it's just 0. So okay. So I call it the algebra, right? There's some product structure that I won't really have time to talk about at all. But at least as a basis, these are all the elements. And the remark that I want to make, this is a finite basis, right? Only finitely many for any fixed GNN. Okay, because at every vertex, you have to satisfy the following condition, right? So remember that the degree of alpha v at every vertex has to be less than or equal to 2 times 3g minus 3. Every vertex. Okay. Right, because if you go about the dimension of the modular space, then you just get 0. Okay, all right. Finally, theorem is that this map from the strata algebra to the cohomology ring, right, which is just if you have a decorated stratum, then by this prescription view it as something on the cohomology ring. It's surjective. Okay, I mean, less fancy words, it just means that these decorated strata give you a basis for the cohomology ring. Okay, give you a Q basis for the cohomology ring. Okay. So to recap, right, what have we done? So we defined this cohomology ring. We defined it as some sort of like some sort of very nice definition, but it was not very useful. We defined it as something that had all the units, so it had all the ones for an MGN bar, and it was closed under push forwards by glowing and forgetful maps. Okay, so once you do that, you actually it's not really clear that it is something that you can work with, but in fact it is, because at the end we found a basis. Right? We found a basis for the tautological ring, which is given by just decorated stable graphs. Okay, now I didn't tell you, well, okay, that's already pretty good, right? But in fact, it's even better. There is some product structure that's pretty explicit. So if you just do like combinatorics of graphs, you can really work with the tautological ring. You can actually do intersections there.
And relations?
Sorry?
The relations.
Yeah, so the relations, it's a good question. I'm not going to say anything about them, unfortunately, but that's a very interesting question. So yeah, this map, it's very far from being an isomorphism. There's many relations in the strata algebra. And these relations are called tautological relations. And it's a very, active field of research, let's say, to like understand things about tautological relations. Okay. There's a conjecture by Pixton that tells tells you what all the tautological relations are conjecturally, but this is still open. But it's good to note that there's really, and you'll see this in the exercises, that there's really like many. I mean, the Q basis there's really tons of relations here, right? This is like much bigger. The number of decorated stable graphs is like way bigger than the dimension of the rings.
So another question is, so what is the difference between, let's say, what are the classes that are not captured by this topological thing? So what is left?
In the cohomology ring, yeah, there's so there are a lot of classes that should be just by dimension counts, that people know that there should be, but really writing some down explicitly is pretty hard. And I think the first example is maybe in like M111, like it's in like, I think it's in like, it's some odd cohomology class. First of all, it's in like in H11, and yeah, you can prove that it's not tautological. But I actually don't know how explicit that is. Yeah. So yeah, I mean, it's known that there should be lots of classes that are not tautological, but you can't really get a handle on them. Okay. All right. So okay, let me tell you at least that one thing that's one of these intersections that's pretty easy, intersecting some sort of stable graphs, which is that if you wanted to intersect a decorated stable graph with just a psi class. Okay. And the key point, yeah, let me just say this again because it's important. The key point to remember is that we have somehow like gone to a smaller ring where you actually can do computations explicitly. We have found the basis of generators, and there's an explicit product between these generators. Okay, so in some example, this is like if I wanted to just intersect I just wanted to intersect this decorated stable graph. So it's in genus 3 with 5 mark points. If you wanted to intersect that with a psi class, say, oh, so maybe I'll put a decoration, right? So let's say put a psi 1, kappa 1, and I want to intersect with that with like a psi class. Okay, this is easy. It's actually just putting the psi class at that vertex. Maybe I call it example or something. Example of intersections, right? 2, 3, 4, 5, and I just put a psi 4 this vertex. Okay. In general, it's a bit more complicated, but not that much more. Okay, great. Finally, we understand the tautological ring, and we would actually like to compute some things in the tautological ring. Questions? This class, well, it has to go on 4, right? So it's a psi 4. It goes with the mark point that it's labeled by. You would get a psi 1 squared. I mean, yeah, so if you intersected with kappa, it means that the kappa would come from some other stable graph, right? It would be associated with the vertex of a stable graph, right? And then you would have to do some, yeah, and then I think it's a bit more complicated. You have to take, yeah, it depends on the graph that it's coming from. You have to take some kind of sum over graphs. So it's combinatorial. Okay, so last part, Newton's conjecture. So really the question that we would like to answer here is like how to compute intersection numbers. Okay. Right. So what are all? We already know what all of our tautological classes look like. They look like decorated stable graphs. Okay. So somehow the first step, right? Someone hands you a tautological class, and you know you want to compute its integral. So it's like alpha. Okay. Well, this is pretty straightforward. It's actually just the integral of all of the alphas Okay, and now we just have to think, okay, well, right, that's great, right? So now we've just reduced everything to computing integrals of these alpha v's, but what are these alpha v's? They're just a bunch of like psi and kappa classes, right? So you actually only need to compute psi and kappa class intersections, and then you're done. So that's step one. Step two, well, I claim that you can remove all kappa classes. And the prescription is the following. Let's say you have a kappa class, called it, and some product of kappa and psi classes. Okay, so let me just call that by Q. Q is going to be a polynomial in kappa and psi's. So this you can actually compute. It's just the this is a fact, maybe proposition fact, something. There's at least a prescription that you can use. Well, actually, this is an exercise. Which is that you put psi n plus 1 to the a plus 1, and you take your Q. Okay. If you see a psi class, you don't do anything. If you see a kappa class, you replace it by kappa class minus psi n plus 1 to the. This is not too hard. This is not too hard to show. I mean, yeah. When I say it's an exercise, I lied a bit. If you already know some things about what happens to, I mean, okay. First of all, somehow, right? How would you try and go about proving something like this? Like, remember that the kappa class is a push forward, right? And the projection formula tells you something like, oh, if I have a push forward of a class, then, I can give that push forward. Like, if I would just change my space, I can give that push forward as a pullback to the thing that's next to it. Okay? And then there's just a little bit of work to show that if you have the pullback of Q, it's equivalent to doing this kind of thing. Okay, this is not very hard. I mean, the first step was like almost trivial, right? The second step is not very hard. So maybe it just as an example of how this works, right? So then what does that mean, right? If I can do this like over and over again, and at some point I remove all of my kappa classes, right? They're all gone. For example, what did I want to do? Kappa 1 squared. Okay, so I'm going to use my prescription. It's kappa 1 times something, some polynomial. So what is this? This is kappa 1 times kappa 1, 0.05 bar. And my prescription tells me, oh, actually replace m05 bar by m06 bar. Replace this kappa 1 by psi n plus 1, so that's 6 to square. For all kappa classes, every kappa class that you see, you should do this. Times, and I see a kappa class, right? And I'm supposed to do that. So I do kappa 1 minus psi 1, 6. Cubed. Right, and I see a kappa class again, and I do the same thing. Sorry. Now I use this formula, and I replace this kappa 1. I have to go up in dimension. Psi 7 squared, 6 squared. just to illustrate that. Okay. So finally, what do we need to do? We actually need to compute psi-class intersections. Okay. And this is hard. And this is really hard. Let's compute for fun some psi-class intersections. I told you in genus 0, right, that psi-classes have some explicit expression. And I told you also how to, the thing that I just erased, like how to intersect psi-classes, just psi-classes with a stable graph. So let me do that. Okay, so what is the last step? Compute kappa, compute psi-class intersection. This is where Witten's conjecture will come in a second. And this is very hard. This is hard. Okay. But let's compute some, or one. One, say two. That's what I wanted to do. Yep. Okay, so now, how am I going to do this, right? I'm in genus 0. In genus 0, psi-classes have some explicit expression. Okay. So I'm going to use that to write my psi1 as as a stable graph. Okay, so that looks like. Now remember, I had to choose 2 other points, right? So we'll choose 2 and 3 in this case, and there's still 4 and 5. Something genus 0, another component genus 0. Put my 1 somewhere. I chose 2 and 3. Put them here. I think that's okay. Yeah, I think. Yeah, if I screw up, then I will do it again. But I think that should be fine. Okay, then there's 4 and 5. So how can I put 4 and 5, right? I mean, remember that this has to get at least one of them, right? So let me put 4 here, 5 here. Well, then of course there's the other one where I put 5 and 4. Right. And then there's one more, which is that I would put 4 and 5 both here. Right? This already have 2 and 3 is enough. Okay. Okay. Now what do I do? What am I supposed to do when I multiply by psi2? I just put psi2 at where I see 2. Okay. Okay, now what? Okay, the first thing to note is that this is 0. Right? Why is that? I have a psi class. This is M04 times M03, and on M03 I put a psi class, right? And M03 is a point. If you put a psi class is sort of in degree 2, but M03 doesn't have degree 2, right? It's just dimension 0. It's a point. So this is 0. Okay. Okay. Now, what is an integral? Integral is just integral of decorated stable graphs. So integral psi1, psi2. Well, it's integrating the class 1 on this component, and it's integrating a psi class here. plus that. Right? It's the same thing. Okay, and we already computed this integral before. Remember, this was 1. So I get 1 plus 1, it's 2. Okay. So you can do computations, genus 0. Okay. All right, as it turns out, this is not, you can't really do these kinds of things in higher genus because, well, you don't know an expression for psi class in terms of like divisors like this. Okay, and then you need something fancy. And this fancy thing is called Witten's conjecture. So finally, as well. Okay, so all right. So this was conjectured by Witten and proved by Kontsevich. And let me tell you what the prescription is. So first of all, like it's typical in physics, you want to actually put all of these psi-class intersection numbers into some generating function. So we define something called the, I guess people call it the Kontsevich-Witten potential, which is just a generating function for psi-class intersection number. Right, so I take all of my psi-class intersections, call it psi1 to the d1, psi2 to the d, psi-n to the dn, or mgn bar, right, where the sum of all the d's is 3g minus 3 plus n, is the dimension. And I put it all into a generating function, right? So I put some variables called t d1 all the way up to t dn. And I introduce some factors that I want, called h bar to the g minus 1 over n factorial. And then I sum. And then I sum over all stable g and n. I write gn, but I always have 2g minus 2 plus n is positive. And then I sum over all the ti's, all the di's that are greater than or equal to 0. So this is a function of infinitely many variables. That's one. Okay, and already from some of the first, okay, and it looks like this. So maybe it's kind of worth writing down. Genus 0, 1 mark point, right? So I have like h bar right here, h bar to the minus 1. So this is encoding all psi-class intersections, right? That's one. And from these, you already see that you can read off some of the intersection numbers. Well, some that we didn't calculate, but some that we calculated, some that Bertrand told you about. So this one as well is the integral of 1 on M03 bar. It's 1. This one is actually the integral of a psi class on M11 bar, 1 over 24. And this one is the integral of a, yeah, so how do I read these off, right? First of all, remember that h bar gives me the genus, so I already know the genus. And then the number of t's gives me the number of mark points. Okay, so you see that the first thing is like t0 cubed, so I have t0, t0, t0. So that's like psi1 to the 0, psi2 to the 0, psi3 to the 0, and M03 bar. That's just 1. Okay, and similarly, you can just, I mean, it's not very hard to see. I guess psi2, psi1, psi2, psi1 squared. Okay. And then I put all of this thing into some generating function called z. And I do some change of variables, which is that I set then tk equals 2k plus 1 double factorial x2k plus 1. Okay. Finally, you can write down the statement of Witten's conjecture. Conservative theorem. I guess I should write is that Z satisfies okay, and in this form, this is not the original form that Witten wrote it down in, but this is the form that's most convenient to compute intersection numbers. These are called Versoror constraints. And this form is due to digraph Verlinde. And what are these Li's? So I is greater than or equal to -1. And these are the Versoror constraints. So Li, the Li's form a representation of the Versoror algebra. So they're going to be, I'll write them down in a second. They're going to be differential operators in the xi, in the x 2k plus 1. And they satisfy the following commutation relations. Okay. And let me write down L and then just say why does this give us all the intersection numbers, right? So Li is, just to get all my factors right here. Okay, this I have to, okay. So I'll write it like using some J's. I kind of tried to stick to like the notation that people use in array structures these days, because I think Renier will talk about something similar, and hopefully some of our notations will match. Where these J's are some differential operators. Okay, so that was a lot to write. So let me say, well, what was the point, right? So we wanted to compute psi-class intersection numbers. We put them all into a generating function, and we said that this generating function actually satisfies some conditions that are called Versoror constraints. These are called Versoror constraints. And these Versoror constraints were some sort of, yeah, thanks. Delta K0. Delta M0. Delta M0. Okay. Yeah, I messed up notation. Ah, oh my God. I'm sorry. Yeah, I don't know what I was thinking. Okay, yeah, so okay, what are the LIs? There are some differential operators. They're pretty explicit. They're given like these, right? And they satisfy, they are a representation of the Virasoro algebra. Yeah, so I'll still say Virasoro algebra just because in fact you can complete these two things that are like go all the way to negative infinity. So I only wrote down the ones, well in fact it's the same formula. And if you would take just the same formula and you take m to be all integers, you would actually get a Virasoro algebra with central charge 1. So I think it's still okay. But it's true that if you would only take these, of course you don't see the central charge, so it's just the bit algebra. Okay. Right. Yeah, and so okay, and there are some explicit differential operators, right? And the main point is that this allows us to compute all intersection numbers. Okay. So the key point here is that Virasoro constraints give a recursive formula for psi class intersections. And the recursion is on the integer 2g minus 2 plus n. So it's very much like the topological recursion. Right. And so if you just know sort of the initial conditions, right, which is when 2g minus 2 plus n is 1, so on 0, 3, and 1, 1. Right, so i.e. knowing that 1 and 0, 3 bar and the only non-trivial intersection numbers, right, bar is 1 over 24, allows us to compute everything. Okay, using these Virasoro constraints. Okay. Okay, I want to write down what some of the recursive formulas that you get are. Okay, and maybe a word on how you're supposed to like think about what these Virasoro constraints are. I mean, everything is like a formal power series. The way that you think about it is that this is 0 in like an h bar gave you some sort of like degree ordering, and so you would act on the z's and like say that in every order up to h bar, all of the things in every degree of h bar has to vanish. Okay, and so in every degree of h bar you get some recursion relations. Okay, so if you do this now for L minus 1 z equals 0, I won't do this explicitly, but it's a very good exercise to do this. So the first thing that you see is that you actually do get the initial conditions as well. Okay. So that's also encoded in there in the Virasoro constraints, first of all. And then you get what people call the string equation. The string equation is the following thing. If you didn't have a psi n plus 1, okay, this is actually a sum over I from 1 to n. Every psi class that you see, you take 1 power out of it. Okay, so from the ith one, on MGN. It's okay, right? Okay. Great. So if you didn't have a psi n plus 1 here, right? So psi n plus 1 to the 0, then you can actually reduce it to some integrals on MGN bar, and see that this is a recursion, right? So this had 2g minus 2 plus n equals 2g minus 2 plus n plus 1, and this side has 2g minus 2 plus n. Okay. You went down in the negative of the Euler characteristic. Okay, and then so that's sort of the first one, right? First one that we have. The second one actually gives you the other initial condition. And the so-called dilaton equation. And this one says that, sorry, mg n plus 1 bar, psi 1 to the d1, psi n to the dn. And if I would just have one psi n plus 1 class, this is 2g minus 2 plus n. And you can remove that psi class. And if you've seen like topological recursion formulas before and played around with them, you'll see that, well, they're actually like very, very, very similar. Okay. In fact, they're, in some case, they're actually exactly the same. And Batan already talked about this. And let me just remind you what that was. Okay, and in general, it's an exercise. These are also exercises. Actually prove these. These are not very hard, but they're nice to do. And in general, if I have Li times z, not minus 1, 0, but something higher, find a recursive formula for the psi class integrals. Okay. Okay, so and then I think the last thing that I want to say is the connection to topological recursion. Yeah. Yes. No, I was not going to talk about that. Yeah, I agree. But just because I wanted to just talk about how to compute psi class intersection numbers, I kind of didn't want to get into this whole KDV Versor equivalence. But I agree that there's some, the original formulation of Witten's conjecture is not really in this at all. But this is the form that you would use if you wanted to compute intersection numbers. And so, I mean, Witten's conjecture has a few proofs, and I mean they're all hard. And it's a very deep statement. Like, I mean, as you can see, like even written in terms of these like Versor constraints, I mean, there's really no reason that you should ever have expected that, you know, if I had like integrals of psi classes, like what do they have to do with the Versor algebra? Right? Why should such a thing exist at all? Not clear, at least to me. Okay. So the last thing that I have 20 minutes, right? Okay. The last thing I want to talk about is some connections to TR. So recall from Bertrand's lectures, right? We had this Airy curve. Can't remember if you called it the Airy curve. You did, yeah. That was the curve. It's on P1, right? Our spectral curve is P1. X is z squared over 2. Y is, I just changed some factors, I think just to get the formulas like I wanted them. But you see it's z squared and z, and omega 0, 2, z1, z2, dz1, dz2 over z1 minus z2 squared. And there was this topological equation formula that produced these correlators, right? These omega GNs. Okay. In fact, the topological equation formula, I think Bertrand already said this, is equivalent to the Virasoro constraints. It's not. I mean, it's a bit of a nightmare to get everything correct, but it's not very hard to derive from the topological equation formula the Virasoro constraints, or even to go the other way back. It's just if you would just lock yourself up in a room for like a day and you just really tried this, you would get it for sure. Okay, in this case, so get the factors correct. Okay, so I guess I should call this theorem of oh, but I think before that, let me say, okay, first of all, and then remember that there was this property that the omega GNs only had poles to the ramification points, right? And the ramification points here are just z equals 0. Okay, so again, this just gives me some chance to introduce some notation that I think you will again see in like Reinier's talk. So let me write down this decomposition and call the coefficients here FGN. Oh, and remember that there was this property that that only like even things appear here, odd differentials. Okay, and then the theorem is that these FGNs are exactly psi-class intersection numbers. You're not happy? No, I fixed the power of 2 and the -1 should be gone because of this. I hope this is true. I tried to make sure that all the factors are correct, and I think they are. So, but if not, please let me know. Okay. Yeah, so that's why I have this like minus sign here and this 2 here and stuff. So this formula is clean now. Okay, great. So what have we discovered, right? We've discovered that actually topological equation, in fact, calculates all psi-class intersection numbers. Right? And the recursive formula is equivalent to the Virasoro constraints, which is a formulation of Witten's conjecture. Okay, but there are some. Yeah. So topological equation, well, in fact, applies to. Well, this is somehow like the easiest example, right, of the spectral curve. And you could ask, like, what happens, right, if I would look at some more complicated examples? Is there still some connection like this? And the answer is yes. Unfortunately, I won't have time to like really talk about the general story, but I want to at least tell you what happens if I would take more or less the area curve and just deform y. Okay, and in this case, things are not so bad. So I want to take, again, a bit of. So was that clear? I guess Bertrand already talked about this, but still, just to. Okay. So slightly more generally. The x is z squared over 2. Y is minus z. I take the same omega 0 too. Okay, then this is a formula due to Bertrand. Call it theorem. Is that I do the same decomposition, right? Remember that I still only have poles with ramification points, so that's just z equals 0. Exactly the same decomposition holds. And then there's a formula for the FGNs. Which is okay. So all I've done is that I've taken the area curve, but I've added like higher powers of z. And these are the things that Bertrand called times. I think the deformation. Sorry. This was the exercise. Great. So now you see the solution to the exercise. Okay, so my k's and kappas are going to look a little bit similar, but this is a KL times kappa L. This was the exercise, or more or less. I see. Okay. Okay, where have all these k's, and these k's are just given by some expression. You can compute. Yeah, so the capital K's, I will just tell. I was just about to say that. Is that the capital K's So you can calculate the capital K's using this formula here. So yeah. 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 Yeah, I know. That's yeah, I know. Can someone suggest a letter? Sorry? Typography, yeah. Let me call it T hat K. T hat L. Great. There you go. Thanks. Okay, so you can compute these T hat L's just from this formula. Yeah. Okay. maybe something to note here is that only odd powers of z appear here, right? And that's actually just due to properties of the topological equation formula. Remember there's a involution on the spectral curve, right? Here it's just z goes to minus z. And because of that, just everything else here that you add and like even add as coefficients of even powers of z, they just drop out, they just disappear. All right. Okay, I think I did better on time today than yesterday. So I think I'll just like kind of wrap it up by saying a few things about that this formula generalizes quite a bit. So the first thing that you can ask for, right, is like, well, what if omega 02 is not actually exactly like this, but it has some things? And Bertrand talked about this a little bit. I don't know if you talked about the intersection theory part of the story. No. Okay, and then there's some yeah, and there's some formula. Okay, and there's some formula that is very similar, looking to this. And in general, and so that's only one of the things, right? And this was a very, very easy example, right? This was a spectral curve that had only one ramification point. Now you could ask, oh, what happens if I have multiple ramification points? Is there some relationship to the intersection theory on MGN bar? Okay, and the answer is also true. And maybe one sort of remark that I should make is that actually this guy is a cohomological field theory. I unfortunately didn't have any time to talk about this. Of rank 1. And if I had a spectral curve with more ramification points, the thing that I should put here, right, before putting these psi classes, would be a cohomological field theory of higher rank. It's more complicated, which is why I didn't really have a chance to talk about it. But it's very explicit. If you know a little bit about cohomological field theories already, you'll know that maybe know also that semi-simple cohomological field theories are completely classified by given Telemon, and there is an explicit formula for for all semi-simple cohomological field theories, which is just written as some sort of expression as the sum over stable graphs. And in fact, that expression you can recover by computing the ingredients of the given Tell reconstruction theorem purely from like the data of the spectral curve. Okay. And in general, if you had a spectral curve with, say, R ramification points, you would get a cohomological field theory of rank R. Always semi-simple. Okay, and this general thing is due to, maybe I can at least just give you a reference to is it capital like hyphenated or something? And it's also in some work of Baynard. I can tell you the papers. I didn't read them exactly, the archive. Right. So actually, yeah, the relationship that we saw here at the end actually extends much further. It extends to a relationship between all semi-simple cohomological field theories and some version of the topological division. Okay. So if any of that like interests you, I mean, feel free to ask me, or there's various other people here that know a lot about it. And I'll stop here. Thanks.
should be exercise tested. So let's say Nitin again. And now go check the data. And we can go to the swimming pool, like here.
We need to change to the swimsuit.
No.